Jai Hind. Myself, Dr. Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. Today, I have taken the topic from the first unit of Fundamentals of Electronics Engineering, the subject code being BC101. So, we will discuss the clipper circuit. The clipper circuit. The clipper circuits have the ability to clip some portion of any given input waveform. Okay. The clipper circuit is made up of resistors and diode. Okay, we can orient the diode in various positions in the circuit, and accordingly the output comes, and some positive part or some negative part, or even maybe the whole positive and negative parts can be clipped off by these particular circuits. Right. So it consists of linear element like resistor, as well as it is consisting of non-linear element like diode. Okay. So there are basically two categories for which we generally study the clipper circuit. The first is the series clippers, and the second one is the parallel clipper, right? So in the series clipper, what we take is we take the output across the resistance. Okay. Whereas in the parallel circuit, we take the output across the diode. So this is the basic difference between the series and the parallel clipper circuits, right? Like here, we can take an example of a simple series clipper circuit. So as we can see in this diagram, it's a simple series clipper, and the input waveform is sinusoidal waveform. The peak of the input waveform is Vm, and this is the negative peak, that is minus Vm. So this is the sinusoidal waveform, and this waveform has been applied to the input terminals of these two. Now here, it is very important to perform the numerical. First of all, we should be very clear about the sign conventions, whatever which we are taking. Like, let us assume this terminal to be positive and this terminal to be negative, right? If this terminal is positive and this terminal is negative, when the positive peak of the waveform, the positive portion of the waveform is inputted to the circuit, then the diode will be obviously reverse, because here the values are positive and these positive values are connected to the N type of the diode. So we should be very clear that this is P and this is N, right? So if the positive value is there, then this diode will be reversed bias. Okay, this diode will be reversed bias, and when the diode is reversed bias, it should behave like open circuit. Now the output, while we are dealing with the output too, we have to be very clear with the sign conventions. Like, it is customary that we take the positive terminal at the upper side and the negative terminal at the lower side of the resistance, right? So first of all, be very, very sure about the positive and negative terminal of any component. So it is up to you how you define your the sign conventions. This is way that by default we take positive and negative like this only. So I will suggest you to take the positive and negative terminal only in this direction, right? Now again, so while we are dealing with the subject, so with this particular numerical, what we do is, there are three diodes, okay, which you can encounter with in the numericals. First is ideal diode, second is silicon, and third is आपका germanium, right? So there are three diodes, and these three diode behaves in a different behave in a very different manner while they are forward or reverse biased. So if I am taking ideal diode, in this numerical we have taken the diode to be ideal, right? This diode is ideal. So ideal diode in reverse bias condition, it behaves as open circuit. The ideal diode in forward bias condition, it behaves as short circuit. Okay, this should be very clear, right? And if silicon diode is there, then in reverse bias silicon diode is open circuit, but when it is forward bias, it can be replaced by the battery of 0.7 volt. And same applies with the germanium too. That germanium diode, while reverse bias, it is acting as open circuit, and germanium diode, when it is forward bias, it is replaced by a battery of 0.3 volts. So in this diode, in this particular numerical, this diode is ideal, right? If this diode is ideal, okay, then while reverse bias, it is open circuit, and forward bias, it is short circuit. So when the positive peak, case 1, the input is positive, okay, input is positive, the diode is reverse bias because the values are positive for this cycle, positive half cycle. So this is the resistance R. So if this is open circuit for the reverse bias condition, then what is going to happen? There is no current. So I is equal to 0. If I is equal to 0, then VU must be equal to 0. Okay. So the case 1, when the voltage is positive, always positive in the positive half cycle, the output across the diode is 0, right? Now coming to the case 2. When the input is at its negative cycle, okay. Now this is negative, this is connected to the end terminal, so diode is short circuited. So we can see that whatever is the input, this will totally appear across the output. So the output will be same as input. Okay, the output will be same as input. Now we will finally conclude the result. This is our VO, okay. For the positive half cycle, the output is 0, and for the negative half cycle, the output is equal to, okay. So here, this is the answer. The positive part has been clipped off by the diode, but it is for ideal diode. Okay. Now coming to the next numerical, the biased series clipper. Okay. In this, what we are going to do, it's a series clipper because output we are taking again across the resistance. But here we have did some biasing to the diode, and this particular biasing is is the negative terminal is connected to the P of the diode, and hence this particular voltage which has been connected with the in series with the diode, this is reverse biasing this diode. Okay, because negative terminal is connected to my P terminal of the diode. Now we have given the input waveform. So this is reversing, and while the positive is connected to this positive terminal, so this will try to forward it, but this is reversing. Okay, so by what time the diode will be getting forward bias? It will be reverse biased up till unless the Vi value is higher than V. The constant DC voltage is V, and when Vi goes up the V voltage, then only this diode can be made forward biased. Otherwise, it will remain. Whenever the input voltage is below the DC voltage V, the diode will be reversed bias. So there are cases. We have to see which part of the waveform is greater than capital V, or which part of the waveform is lower than capital V or DC voltage, right? So coming to this case 1, so here we will mark a value V. Okay, so this value V, the input waveform is below V for this portion, and the input waveform is greater than V for this portion. Okay, so for these green portions, the diode is obviously, this is reversed bias, and only for the red region of the input waveform, the diode will be forward biased, because the input voltage is greater than the DC voltage V. So we have two cases: input voltage is less than V and input voltage is greater than capital V. Since it's an ideal diode, so we will put the diode to be in short circuit when the diode is forward bias, and we will put the diode in open circuit when it is reversed bias, because it is ideal diode, right? Be very, very careful. The diodes will be obviously silicon and germanium, then the cases may increase. So case 1, when Vi input voltage is less than V, right? So what the diode will work? For Vi less than V, it is forward reverse biased. And for this, okay, again current I is equal to 0 and the output voltage VO is equal to 0, because the current is 0, right? Now case 2. The diode will be short circuited for this region. Okay, then what should be the output voltage? So we have the sign convention. We will apply the KVL rules, right? So this is our Vi, So we will put the KVL, applying KVL in this loop. Okay, so by KVL in the loop, we have plus VI minus V minus VO is equal to 0. So VO is equal to VI minus V. Okay. So we have two cases. One, when the input voltage is less than capital V and the input voltage is greater than capital V. Now, we have discussed both we have made the circuits very clearly, and now we have applied KVL in the second case. Okay, this case is very simple. Here the output is 0 because there is no current. The diode is open circuit. Now here we have found the value of VO is equal to VI minus V. Now the question arises, how we will find the maximum value of the diode? So what is going to happen? Some portion of the waveform to be clipped off. So how we will make the waveform? Just please listen here very carefully. Just have a raw sketch of the input waveform. Okay, mark the V value. Okay, this is the portion where the diode is reverse bias. Okay, so again mark at this value. Now I am plotting it with my red. Okay, so at this portion the diode is reverse biased and we can see the output is 0. At this portion the diode is reverse biased and we can see the output is 0. Okay, this portion also the diode remains in reverse bias and this output waveform is 0, right? Now, so what would happen? The output is VO VI minus V. So we have to very careful. Then suppose that this is Vm because the peak value of the waveform is Vm. Now the peak value of the waveform is going down by V. When the diode is forward bias, the output voltage is like that. The waveform, input waveform is down by capital V. So we will start this waveform here. Okay. And Vi minus V. Okay. So when this Vi is here, Vi is equal to V, the output should be 0. So here the output should be 0 and this should be the final waveform of the circuit. Okay. See, when Vi at this particular point, Vi is equal to V. Okay. Then V minus V is 0. So at this particular point also Vi is equal to V. The output voltage is this is the graph for the output voltage. So this is 0. Now the peak value is going down by V. Okay, Vm minus V. So when Vm minus V, that means this Vm, this is V and this will go down by Vm minus V. Okay. So this is how the waveform will be made. Okay. When this is Vm, if Vm is equal to V, then it will be like exactly this. Otherwise, there are again 2 to 3 cases that this value V is less than Vm. So it will obviously approach. Okay. It will obviously approach to some value greater than V. Okay. So how you are going to make the circuit for the diode, and this particular value is nothing but Vm minus V, and that will depend purely upon the value of the capital V. Okay, if the V, capital V is 2 volts and the maximum is 5, then this will go to 3 volts, right? So maximum will be the 3 volts. So here this is the biased series clipper for ideal diode. Similarly, we have another example for so many series clippers. Here in this circuit, I will brief all these circuits in short, that here whatever we did is this particular we have got, and in the biased series clipper, this particular waveform which we have done, all the outputs for the series clipper we are taking across the resistance R, okay, and doing it ideal. In all the cases we have taken all the diodes in all the circuits are, you know, the ideal ones, right? So there are 6 basic circuits of series clippers which we need to study, and the concept will be same as told earlier, and you have to practice all these circuits for commanding the series clippers, right? Now coming to some parallel clippers, we will also do one or numerical from the parallel clippers. The parallel clippers are different to the series clipper. Why? Because we are taking the output across the diode. Here we are taking the output across the diode. Let us see how it is going to work. Again, the sign conventions we will take earlier in advance so that we should not make any mistake for the output voltage, right? Now here, let us do for the positive half cycle. For the positive half cycle, the positive peak is connected to the positive P of the diode, so it will be forward bias. So we will take for this particular, we will do it a little fast, okay. So in this region all the values are positive, and these positive values are making the diode to be forward bias here, plus minus. So here the circuit is short, the R is 0, I is flowing in this case, but the circuit is short, so there is R0 and making output voltage to be 0. Okay. Similarly, we will discuss case 2, and we should be very clear for the negative half cycle. The diode is open circuited because this P side is connected to the negative part of the waveform. Okay. So for this case, right, and this is the output voltage. Now for this R, there is no current, so this voltage is 0. Okay, the voltage across this is 0 volt, and all the voltage in waveform, all the voltage of the input will be appearing across the output port only. Because voltage, whatever is the voltage will appear, all the voltage will appear across the output terminal, and VO will be equal to VI, and that will be the right. So final waveform we will definitely make, and the final waveform will be, here is the output and this is the T, and for the positive half cycle this is 0, okay, and after that this is the waveform. Okay, VO is equal to VI, here this is minus V, and you can mention it. So this is how the parallel clipper will work. See, there is no basic difference in the functioning of clipper and clamper. It is just that you have to apply the Kirchhoff voltage law, obviously, and be sure, be very, very sure that how you are taking the diode in forward bias and reverse bias, and you should know the rules that if ideal diode is there, it is short circuited, the diode will be short circuited under forward bias, open circuited under reverse bias. For silicon diode, the diode is short circuited, not short circuited, but it is open circuited while reverse bias, and a 0.7 battery according to the diode terminal, right, in the forward bias condition, and it will get forward bias after the voltage it gets equal to 0.7 or greater than 0.7, right. Similarly for germanium diode, if it is forward bias, then it will be forward bias when the voltage across the germanium diode will equal to 0.3 volts or greater than 0.3 volts, right. So do this numericals with silicon diodes and germanium diode too, and then get the output and compare how the voltages are appearing across the diode, and how you are clipping the various portions of the waveform according to the circuit conditions, right. So there are bias clippers too, but again I have mentioned parallel clippers, and in all the parallel clippers we are taking the output across the diode, and in these two circuits the diodes are not biased, but in all four circuits the diodes are biased, and you can perform by the same concept and you can get the result for the parallel clipper circuit. Now some more examples for the parallel clipper here in this circuit. See, there are two diodes and both the diodes are biased, right. There are two diodes and both diodes are biased. This particular diode and both the diodes are ideal, as there is nowhere written in this numerical that these diodes are of silicon or germanium. So you have to consider it as ideal diodes, right. These as ideal diodes, and here this is biased by V1, this is biased by V2. For positive half cycle, okay, for positive half cycle, this is making it a reverse, this is making it reverse. Both the diodes are being reversed by the biasing voltages. If these both the diodes are being reversed by the biasing voltage, then see what is happening. This diode, this voltage is making it forward, this voltage is also making it forward. When Vi is less than V1, when Vi is less than V1, okay, then what is going to happen? When Vi is less than V1, this diode will be forward biased and it will act as short circuit, okay. And since Vi is positive, this diode will be reverse biased. Only this diode will work and the voltage across it will be V1, okay, right. The voltage across will be V1, right. So here we have to increase this voltage Vi to be greater than V1 to make it forward bias. If it is forward bias, since the positive terminal is connected to negative terminal, this will be reverse bias and open circuited. So this circuit will not work. Only this will work and the output will be equal to V1 between these two ports when this diode is forward bias. And when it will be forward bias, it will be forward bias when Vi is greater than V1. So here Vi is greater than V1 and this diode is forward bias and the voltage is V1, okay. And this diode will be forward biased when input voltage in the negative side, it will be greater than V2, okay. So in this portion, this is greater than V2 and hence this voltage is V2. So I have considered the cases when these two diodes were forward biased. When what will happen when any of the diode, let's say this voltage is below V1, this is open circuit, but this is this when this voltage is less than V1, this will be open circuited, only this will work. And when this is like the case here, this waveform, let us mark it V1, okay, and this is a minus V2, okay. For this particular waveform, this portion of the waveform, when this is positive, and this voltage is but less than V1. So when it is less than voltage V1, then it is open circuit, okay. Similarly, for this particular, this is again this output waveform. This output waveform is again it is for this particular waveform. This is again reverse biasing. It is also reverse biasing, so it is also open circuited, and the input waveform will be equal to output waveform, and hence I have made this particular portion to be same as the input waveform. So by doing all these exercises, we can understand how the diodes are working as clipper circuit. These are not practices. These are not very simple circuits, but we need to practice. And whatever the questions have been given, all the circuits, just go through all the circuits, do yourself, and then you will understand how the clippers are working. And later on, you have to replace all these diodes by silicon or germanium, and then get the outputs as well. Jai Hind. Thank you.